Hello friends, welcome back. In this tutorial we will study about Banker's algorithm. Actually this Banker's algorithm is a deadlock avoidance algorithm. In previous tutorial we studied about resource allocation graph algorithm. This resource allocation graph algorithm is not applicable to a resource allocation system with multiple instances of each resource type, right? So in that cases where resource allocation system is with multiple instances of each resource type, we use Banker's algorithm, right? So in Banker's algorithm, what happens? It is a deadlock avoidance algorithm, and in this algorithm, when a process requests a set of resources, the system determines whether the allocation of these resources will leave the system in safe state or not. So the resource will be allocated if it leaves the system in safe state. Otherwise, the process will have to wait, right? So to implement this Banker's algorithm, we need to maintain many data structures, right? Now suppose there are n processes in the system, p1, p2, p3, so on up to pn, and there are m resource types, right? r1, r2, r3, so on up to rm, right? So we need to maintain a vector of length m available, right? Available is a vector of length m, right? And if available, j is equal to k, right? If available value in this vector, right, in vector available at index j is equal to k, then it means that k instances of resource type rj are available, right? Now another is max, right? It is a n cross m matrix, and it specifies the maximum demand of each process, right? If in this matrix the value at ith row and jth column is k, then it indicates that a process pi may request at most k instances of resource type rj. Another is allocation, right? So what is this allocation? It is a n cross m matrix, and it defines the number of resources of each type currently allocated to each process. So if in this allocation matrix the entry at ith row and jth column is k, then it means that the process pi is allocated k instances of resource type rj, right? Now another is need. It is also a n cross m matrix. Need is a n cross m matrix, and it indicates the remaining resource need of each process, right? If in this matrix need the value at ith row and jth column is k, then it means that process pi may need k more instances of resource type rj, right? So value at ith row and jth column in matrix need is equal to the value at ith row and jth column in matrix max minus the value is stored in allocation matrix at ith row and jth column, right? Now each row of matrices allocation and need is considered as a vector, right? Allocation I, right? Allocation I represents the ith row of allocation matrix, and it specifies the resource currently allocated to process pi, right? Need I, right? This need I represents the ith row of need matrix, and it specifies the additional resources that process pi may still request to complete its task. Now suppose there are two vectors of length n, right? Vector a and vector b. Then the vector a is said to be less than or equal to vector b if ai is less than or equal to bi for all I is equal to 1, 2, 3, so on up to n, right? So it means if there are two vectors of length n, vector a and b, then the vector a is said to be less than or equal to vector b if at every index I, right? If at every index I the value stored in vector a, right, is less than or equal to the value stored in vector b at the same index I. Now as I have told you earlier that this Banker's algorithm is a deadlock avoidance algorithm. So in this algorithm, what happens when a process requests some resources, right? Then before allocating the resource to the process, it is determined that after allocating the resources that the system will remain in safe state or not. If after allocating the resources to the process, the system will remain in safe state, then the resource will be allocated to the process. Otherwise, the process will have to wait, right? Now, in Banker's algorithm, how we find that the system is in safe state or not, right? So in Banker's algorithm, to find the system that whether it is in safe state or not, right? This algorithm is used, right? So in Banker algorithm, this is the way to find out whether the system is in safe state or not, right? This algorithm is used to find whether the system is in safe state or not, right? So what happens, suppose there are n processes in the system, p1, p2, p3, so on up to pn, and there are m resource types in the system, r1, r2, r3, so on up to rm. So what happens, we use two vectors, work and finish. Work is a vector of length m, right, where m is the number of resource types, and finish is the vector of length n is the number of processes. Then what we do, we will initialize these vectors, work and finish, right? Work is initialized, right, like this. Value of vector available is assigned to this vector work, right? And how this vector finish is initialized, at every index I, right? In this vector finish, the value false is set, right? So finish I is equal to false for all I is equal to 1, 2, 3, so on up to n. So at every index, the value false is stored in this vector finish, right? Now what is the next step? The next step is, after that we need to find an index I such that finish I is equal to false and need I is less than equal to work, right? So what happens, we need to find an index I, right, which will satisfy these two conditions, right? What is the first condition? The first condition is that at index I in vector finish, the value should be false, and the second condition is that need I is less than equal to work. It means the need of process pi should be less than or equal to work, right? If no such I exists, right, if there is no index I, right, then what will happen, we will go to step 4, right? What happens in step 4? In step 4, it is checked if finish I is equal to true for all I, then the system is in safe state, right? So when we go to step 4, what happens, it is checked that in vector finish, right, whether all values are true, right? In vector finish, at every index, whether all values are true, right? If the all values are true, right, it means that the system is in safe state. Otherwise the system is not in safe state, right? So this will happen if we do not find such index I in step 2, right? If we do not find such index I in step 2, right? But if we find such index I, right, then what we will do, if such index I is found which will satisfy these two properties which are specified in step 2, then what will happen, we will move to step 3, right? We will not move to step 4. What happens in step 3? In step 3, what happens, the work will be set to work plus allocation I, right? The value of this vector work, it will be updated, right? So in that, what happens, whatever the resources are allocated to process pi, right, it means ith row of allocation matrix, ith row of allocation matrix, it is added to the work vector, right? And finish I is set to true, right? In finish vector, the value at ith index is set to true, right? And then go to step 2, and then after that again control will go to step 2, right? Again we will find another index I which will satisfy these two properties, right? Let us see how this algorithm works. Suppose there are 5 processes in the system, P1, P2, P3, so on up to P5, and there are 3 resource types A, B, C. This is the allocation matrix, right? Now here you can see that process P1 is allocated 0 instance of resource type A, and process P1 is allocated 1 instance of resource type B, and it is allocated 0 instance of resource type C, right? This is the allocation matrix. This is the need matrix. In need matrix you can see that the process P1 needs 7 instances of resource type A, right? And it needs 4 instances of resource type B and 3 instances of resource type C. And this is the available vector, right? This is the available vector. Here you can see that 3 instances of resource type A are available, and 3 instances of resource type B are available, and 2 instances of resource type C are available. So what is the first step of the algorithm? In first step, what we need to do, we need to take 2 vectors, work and finish, right? And we have to initialize them. So here we will take finish vector of length 5, because here there are 5 processes, and we will take work vector of length 3, right? Because here there are 3 resource types A, B, C, right? So what happens, initially we will set finish I is equal to false for all I is equal to 1, 2, 3, 4, 5, right? So it means how we will initialize this finish vector. At every index of this finish vector we will set the value false, right? And this work vector, right, to it we will assign the value of available vector, right? Now what is the second step of the algorithm? Second step of the algorithm is we have to find an index I such that it satisfies these 2 conditions, that finish I should be equal to false, right? And need I should be less than or equal to work, right? So here we have already set the value of work vector, right? To it we have assigned the value of available vector. So now the value of work vector is 3, 3, 2 at index A, right? The value 3 is there for index B, the value 3 is there for index C, the value is 2, right? So we have to find the row of a need matrix whose value is less than or equal to work vector, right? So here see this row, second row of need matrix, it is 1, 2, 2, right? And this fourth row of need matrix, right? These two satisfy the conditions that their value is less than or equal to work, right? Actually their value is less than work vector, right? So we have chosen this index 2, right? So what happens in this case, we have chosen this index 2, right? So you can see that need 2 means second row of need matrix, right? It satisfies this condition that need 2 is less than or equal to work, right? And you can see that finish 2 is also equal to false. These 2 conditions are satisfied, right? So now what we have to do, we have to update the work vector, right? So we will update the work vector. How? To work vector we will add the second row of allocation matrix. So the second row of allocation matrix is 2, 0, 0. So this value we will add to the work vector, right? So when we add this value 2, 0, 0 to the work vector, the new value of the work vector is 5, 3, 2, right? This one, right? And after that what we need to do, we need to set finish 2 is equal to true, right? Then again we have to repeat this second step, right? Again we have to find an index which will satisfy these 2 conditions, right? So now the value of work vector is 5, 3, 2, right? So here now you can see that one is this row, right? And this row also, right? So they satisfies both the conditions, these 2 rows, right? they satisfies both the conditions which are specified in second step of algorithm, right? So this is the fourth row and this is the fifth row, so we will consider only the fourth row, right? So we will consider the index 4, right? So you can see that need 4 is less than or equal to work, it satisfies this condition, right? And finish 4 is equal to false, so these two conditions are satisfied. So what we need to do, we need to update the work vector, right? So to work vector we need to add the fourth row of allocation matrix, right? Because we are considering this index 4, right? We are considering this fourth row of need matrix, right? So when we add this fourth row of allocation matrix, that is 2 1 1 2 1 1 to the work vector, then the new value of work vector will be 7 4 3, right? 7 4 3, and after that we will set finish 4 is equal to true, right? So finish 4 is set to true, right? Now again we have to search the index which will satisfy the two conditions which are here, that need I is less than equal to work, right? And finish I is equal to false, right? Now the value of work vector is 7 4 5. So you can see that the value of this row is less than the work vector, right? Value of this row is also less than work vector, and value of this row is also satisfies the condition that it is less than or equal to work vector, right? So among these three, right, we can choose any one of them. So here I have chosen fifth row of need matrix, right? So need 5, I have chosen the fifth index. So you can see that need 5 satisfies the condition less than or equal to work, right? And finish 5 is also false, right? Its value is false. So since both the conditions are satisfied, we will update the value of work and we will set finish 5 is equal to true, right? So here to work vector we will add the allocation 5, that is fifth row of allocation matrix, that is 0 0 2, right? So when we add 0 0 2 to work vector, then the new value of work vector will be 7 4 5, right? And after that we will set finish 5 is equal to true, right? Now again we have to find the index I, which will satisfy the both conditions of which are specified in second step of algorithm, right? Now you can see that the value of a work vector is 7 4 5, right? So first we start from need matrix, right? So here you can see that this for index 2 4 and 5. So for 2 4 and 5, for them finish I is set to true, right? So finish 2 is not false, finish 4 is not false, finish 5 is not false, right? So these rows we will not consider, right? Because these index we have already processed 2 4 and 5, right? For them we have already set finish I to true, right? At that indexes we have already set the value true in finish vector, right? So these two rows are remaining in need matrix, so we will consider only these two indexes, index 1 and index 3. Now see the third row of need matrix, right? Its value is 6 0 0, right? And the value of work vector is 7 4 5, right? So what happens, the third row of need matrix, right, it satisfies this condition, need 3 is less than or equal to work, right? This condition is satisfied, and finish 3 is equal to false, right? This condition is also satisfied, right? In finish vector the value at third index is already false. So since these two conditions are satisfied, what we will do, we will update the value of work vector, right? To work vector we will add the third row of allocation matrix. So the third row of allocation matrix is 3 0 2, right? So when we add this value 3 0 2, the new value of work vector is 10 4 7, right? And then we will set finish 3 is equal to true, right? Now again we have to repeat the second step of algorithm. We have to find the index I, right, such that need I is less than or equal to work and finish I is equal to false, right. So now these two conditions can be satisfied only by the index 1, right. You can see that first row of need matrix, its value is 743, right. So 743, so this value satisfies this condition that need 1 is less than or equal to work, right, and value in finish vector at index 1 is false. So both the conditions are satisfied. So here we will update the value of work vector. To work vector we will add the first row of allocation matrix. So first row of allocation matrix is 0 1 0. So when we add 0 1 0 to work vector, so the new value of work vector is 10 5 7, right. Now what we will do in finish vector at index 1, we will set the value true, right. Now again we will repeat second step of algorithm. We have to find the index I which will satisfy these two conditions, right. Now what happens, these two conditions will not be satisfied, right. We will not find any index I which will satisfy these two conditions. So we will go to step 4, right, of the algorithm. We will go to step 4 of the algorithm. So here we will check whether finish I is equal to true for all I, right. So you can see that here there are 5 processes, right. So in what happens in finish vector, there are 5 indexes, 1 2 3 4 5. So here you can see that we have set index 2 also, at index 2 in finish vector the value to true, right, and at index 4 also, at index 5 also, at index 3 also, and at index 1 also, right. We have already set the value true in finish vector. So this condition is satisfied. Finish I is equal to true for all I, right. So therefore what will happen, it means that the system is in safe state, right. Now we have studied that how the Banker's algorithm find out that whether the system is in safe state or not. Now how this Banker's algorithm work. So what happens when some process Pi requests some resources, right, then the request I is the request vector of process Pi which specifies the resources which are requested by the process Pi, right. So in request I vector, right, which specifies the resources which are requested by process Pi, right. If it in that vector at index j the value is k, then it means that process Pi requests k instances of resource type rj. If request I vector is greater than ith row of need matrix which specifies the need of process Pi, then it will raise an error, right. Now if value of a request I vector, right, value of request I vector which specifies the request of process Pi is less than or equal to available vector, then we will go to step 3. Otherwise process Pi has to wait. So what happens in step 3? In step 3 what happens, system pretends to have allocated the requested resources to process Pi by modifying the state as follows, right. So how it modifies the state? First it modifies the available vector, right. From available vector it will subtract the request I vector, and then it to allocation matrix, right, ith row of allocation matrix which specify the resources allocated to process Pi. To that row request I vector will be added. Then need I, right, ith row of need matrix which specifies the need of process Pi, right. From that row we will subtract the request I vector, right. If the resulting resource allocation state is safe, then the process Pi is allocated its resources, right. Otherwise we will not allocate the resources to process Pi. Then the process Pi must wait and old resource allocation state is stored, right? If the resulting resource allocation state is safe, then this transaction is completed, right? And what happens? The process pi is allocated its resources. If this resulting resource allocation state is not safe, then what will happen? That process pi must wait and old resource allocation state is stored.